coming to our project now. Let's have a discussion on our project. Why I'm placing so much emphasis on the project is because the project has a weight of 20%, right? Okay, the project has a weight of 20%. That's an important chunk of your coursework. And it's not a difficult project. It looks difficult, but it's not. If you came to the lecture yesterday, we went through a mini version of the project. And if you have been doing this week's tutorial, if you've done it independently, or if you attended the tutorial and then you were able to follow through what's happening, then yeah, you're pretty much good to go. The only difficult part is this. In question 1, probably what I would suggest is just to get you guys warmed up. What you do is probably start off with problem 2. Right? And in problem 2, the difference is that you only have one flip-flop, one type of flip-flop, not one flip-flop, right? One flip-flop means you've got only one bit, but really you've got a, let's say for the guy number 1, the person number 1, his largest number is G, which is 15. So 15 would occupy 4 bits. 15 is a 4-bit number. So therefore he would need 4 flip-flops. But in solving question 2, there's only one type of flip-flop, which means he would need 4 SR flip-flops, right? Okay, so maybe start off with question 2 because only one type of flip-flop is required. And that's just like our problem which we did yesterday, and just like our problem which we did doing in this week's tutorial. So that will really help you out. Now, if you look at question 1, there's a combination of flip-flops. So you start off with question 2, you get the hang of it. Then based on the same truth table, you just do an extension and you can do this. But there's a combination. So if we look at the guy number 1, question number 1, student number 1, is this here? Oh, the guy in the corner, right? Okay, so we're helping you out. All right, okay, D and JK, all right? So you better get 100%. Okay, all right, okay. Okay, so he is using D and JK. So the guy in question number 1, he has a combination. He's got to use both. And in his case, he's got 15 is the largest number, so that's 4 bits. He needs 4 flip-flops. So what he does is he uses 2 of them should be JK and 2 of them should be D. Yeah? 2 of them should be JK and 2 of them should be D. Now the sequence. Now we've already decided the ratio. 2 of them JK, 2 of them D. Now the sequence, it's up to him. If he wants to put D, D, JK, JK, that's all right. If he wants to put D, JK, D, JK, that's all right. Okay, if he wants to put JK, JK, D, D, that's okay. JK, D, JK, D, that's all right as well. Whichever combination he wants to use, he can use that particular combination of thing. But it's got to be, they've got to maintain the ratio of 2 flip-flops and 2 flip-flops, right? 50-50. If let us say you end up with 5 flip-flops, I don't know if there's any 5 flip-flops here, but anyway, if you end up with 5 flip-flops or 3 flip-flops, let's say 3 flip-flops, right? If it's a 3-bit number, if your largest number is 3-bit, and you end up with only building a 3-bit system, right? So I guess you can't do half and half. 2 will be, let's say, JK and 1 will be D, or 2 will be D and 1 will be JK, all right? Here you get the picture of what I'm trying to say. Now the other point I want to mention over here is your Carnot map. Remember, the first thing which we do is we draw our state diagram. So let's flip over to the problem which we did yesterday, in yesterday's lecture. So just a revision, just a quick revision so that you guys have an idea. So in yesterday's problem we had this sequence. We ended up converting our decimal sequence to binary, right? But note, that binary number, the largest number over here in our sequence was 7, so we use a 3-bit system, right? Largest number is 7, so we use a 3-bit system. Now, the next thing is, if the largest number is a 3-bit system, we go in this direction. So that means we'll use 3 flip-flops. Now, if you look at our table, you've got 3 flip-flops. Now, in your problem, there is X as well. there is X to control the direction, whether you're going clockwise or anti-clockwise, right? System input. Now, if you would have had an X, you see there's 3 inputs over here, and this is the numbering system which I would recommend. Use Q0 because it's a standardized numbering system. You can use QA, QB, QC, QD as well, or QE and all that. That's all right. It'll give you the same answer. The circuit will be the same. But Q0, Q1, Q2, Q3 is more in line with, you know, Q0 being the least significant bit, Q3 being the, or Q4 being the largest, most significant bit. Now, because you had 3 over here, your Carnot map ended up as 3. Now, if there was an X over here to control the direction, let's say X to make it go clockwise, and X equals 0 to make it go clockwise, and X equals 1 to make it go anti-clockwise, that would be, then you would need on this table an X. There would need to be an X over here. So therefore, you'll have 4 inputs, system input plus the current state. And therefore, your Carnot maps will become 4 by 4. So you've got to look out for how many variable Carnot map will you need. And remember, Carnot maps, you can have 2 by 2 Carnot map. It's powers of 2, right? 2 by 2 Carnot map, 4 by 4 Carnot map. Then if you get, let's say, if it's 2 variables, 2 to the power of 2 is 2 by 2, right? 4, right? Okay. 2 variable, you'll need 2 by 2 Carnot map. If it's 3 variable, you'll need 4 by 2 Carnot map because there'll be 8 cells. 2 to the power of 3 equals 8. If it's 4 variables, you'll need 4 by 4, which is 2 to the power of 4 is 16. Yeah? Okay, 4 variable. 2 to the power of 4 is 16, so 4 by 4, that's 16 cells in your Carnot map. If it's 5 variable, you'll have a 32 cell Carnot map. And how do you do a 32 cell Carnot map? You stack 2 by 4s on top of each other. All right? You stack 2 by 4s on top of each other. All right. Okay. So that, I think that will be the challenging part for you guys. And if somebody is unfortunate to have a 6 variable Carnot map, you come and see me and I'll help you out, because then that means you got a extra or 2 extra variables, right? But I think most of you should end up with either a 5 variable Carnot map or a 4 variable Carnot map. All right? Okay. Okay. So let's just just a few notes, some descriptors, eh? So what I've done is the way I teach. See, the good thing about digital electronics, digital logic is that the good thing about digital electronics is that it's like a jigsaw puzzle, right? It's like a jigsaw puzzle. There's all these building blocks and there's all these pieces, okay? And some people, they solve jigsaw puzzles by doing how many of you guys played jigsaw puzzle before? Right, maybe when you were a kid, or, you know, even recently adults played as well. You know, there's large international competitions. They give you a brand new jigsaw puzzle and then the fastest team wins, right? Fastest guy to solve the puzzle wins. All right. Okay. So some people solve jigsaw puzzles by doing the edges first, right? And then moving towards the middle. Some people use colors. So color blue, they try and solve all the color blue, call the color green, and eventually, in the end, the puzzle comes together. Some people go from the middle and they go outwards. So basically, the way I've taught you this digital logic is it's like a jigsaw puzzle. I've taught you the analysis first, then I've taught you design, then I'll teach you a few definitions now, and then I'll teach you how to prove that particular table. I'll teach you this. So let's have a look at our 2018 paper. So the way we went is, I got you to do this. Hey, by the way, this problem was in one of our tutorials recently, right? So this year's tutorial has got last year's problem. So obviously this problem is not coming. All right. Okay. So I taught you analysis, right? Well, in fact, the way I taught you sequential logic was like this. We went through the first flip-flop. We did one flip-flop, the very first one. We said, okay, we learned about the SR latch, the fundamentals, because SR latch is the basis of all those. There's 4 flip-flops which you've learned, right? There's 4 flip-flops. The basic core DNA is the SR latch. From the SR latch, you build the SR flip-flop. From the SR flip-flop, you can build the D flip-flop. So what we did so far is, we've done the SR flip-flop. We went the SR latch, we built the flip-flop, we did the truth table, we did the characteristic table, we did the excitation table, and the characteristic table, and the state diagram is the same thing. So we've done this. And I think we touched a bit on the D flip-flop as well, how to build the D flip-flop, and that's in your tutorial. But I'll cover this part again, how to get the characteristic table and how to get the excitation table. Then from here, you will notice that, hey, Imran did not cover JK flip-flop. How did we build the JK flip-flop? And you will be wondering, what about the T flip-flop? We have not covered the T flip-flop. But we're looking at the tables. Right? So I'll do that later. I'll prove these tables later. Then what I did was I jumped into analysis. We did analysis. Right? We did analysis. After analysis, we did design. After analysis, we did design. Yeah? Okay, so analysis followed by design. All right. Okay. So now you have all the building blocks in place to do the larger problems, right? So you have the knowledge. So basically, when you look at the jigsaw puzzle, we've done the middle part, the hard part is done. If you have understood yesterday's lecture and this week's tutorial, that's the hardest thing you can do, right? Now what we'll do is we'll just do the easy part. We'll just do the edges. You know, the jigsaw puzzle edges is very easy because it's a straight line. You know, okay, this falls on the edge and you just look for another edge which can fit into it. Right? Okay, and if a piece in the middle, it's got 4 connectors. There's one on the top, one on the left, one on the right, one at the bottom. Yeah? And the one on the edge, it's very simple because one side there's no connectors. Yeah? So we've done the middle part. Now we're going to do the easy bits. So I'm going to teach you some definitions now. And then next week, I will prove to you how those flip-flops, the remaining flip-flops. SR, we've done from beginning, from scratch. Remember we were saying, hey, when you know, case 1, case 2, case 3, that was the SR latch. Then after SR latch, we built the SR flip-flop. From the SR flip-flop, we did the truth table. From the truth table, we did the characteristic table. Characteristic table, we got the equation. And also from the characteristic table, we got the excitation table. All right, now, we'll do that for JK and T next week. For now, what we will do is, we'll now move in and have a look at few important points. All right. All right. Now, the first thing I want to talk about is something called milli machine and more machines. All right. Okay. Let me just put it on. So, just a bit of notes. Just maybe 2 definitions, and that will help you to answer. If you look at last year's paper, the first question is deduce whether the system is a milli machine or more machine. Right? Okay. These are a particular classification of a machine. All right. Okay. Another particular type of question is this synchronous machine or is it asynchronous? Right? Remember what I taught you. What does the word synchronous mean? Synchronous means all the clocks are tied together. Right? Which means when the clock pulse triggers it, all the flip-flops, they change state together. Even though you can change your input over here, your J and K, you can change it, but the clock pulse is the one which decides when the final output will change. All right? Okay. Okay, clock triggering. Okay, so first thing we want to talk about is something called milli machines. Milli and more state machines. All right. Now, okay. So let's start off with the first one. What is a Moore machine? What is a Moore circuit? Or what is a Moore What is that? What is a Moore state machine? Okay, it's really simple, right? And it comes down to the state diagrams. All right. maybe even I can give the definition. So for more, the output is a function of the present state only. The output is a function of the present state only. All right. Now let's look at an example, Let's look at an example. Does anyone have the in-class problem which we did? You know, I photocopied something and I gave it to you guys. Just pass me. Okay. All right. So this guy was in class. All right. Okay. All right. Okay, guys. So let me just fold this. Fold it. All right. Okay. I'll fold this. Okay. Now have a look at this second question too. The output is a function. You know, you flip back to your lecture where we did this analysis problem. This is the question 2. Let's look at the definition. The output is a function of the present state only. The output is a function of the present state only. All right? Okay. Now, what do we mean over here? If you look at your particular outputs in this circuit, let's zoom in slightly. Let's zoom in slightly. Okay. All right. Okay. Now, if you look at our particular circuit, how many outputs are there in this circuit? How many outputs? 2 outputs. And the outputs are basically the outputs from the first flip-flop, A flip-flop, and B flip-flop, QA and QB. Right? Now, the outputs are determined by the present state of QA and QB. Can you see that? Right? Okay, the outputs is a function of the present state only. Okay. Okay, now let me just put a note over here. Okay, let's say, I'll just say refer to Q2, rather than redrawing that whole circuit, refer to Q2, all right, in the in-class problem. Now, we've got to make a change. Let me just show you. Assume QA and QB are odd. Okay? So basically we have a new output. Therefore, there's a new output which is Y. Right? Y is equals to A or B. Oh, sorry. QA or QB. Okay, now let me explain this. Okay, let's look at this again one more time. Now, and take into account what I've said over here. If you want, you can redraw this circuit, but you know, we're trying to save time over here. Okay, we're looking at a Moore circuit. Let's say we modify this circuit. Let us say we modify this circuit, right? And from A, we take the A, right? Okay, we take the A, and we take the B, right? And we OR it. So it looks like this. So your QA is here, QB is there, and that's our Y. Alright, you get the picture of what I'm saying now? That's our QA, QB. Now let's modify our circuit to have that. Now, the output is what? The system output is Y. And can you see that the output is a function of the present state only, is a function of QA and QB. Is there any involvement of the system input, X? No, there's no direct involvement. Of course, the system input X is influencing QA and QB. But the system input X, if you look at our circuit over here, if let us say we assume this, let me just put this side by side. Okay. So if we did that, okay. All right, now you guys get the picture now. So if you look at our circuit now, right, the output Y, let's say there's a new output called Y, and Y is equal to A or B, QA or QB. Now if you look at Y in itself, does that have any influence from X, direct influence? No. There is only indirect influence because X is feeding into what? X is feeding into QA and QB, but QA and QB are directly feeding into Y. So this is a Moore machine. Okay, this is a Moore machine. Right? Okay? So let's look at the original statement. Says the output is a function of the present state only. Right? Present state is QA and QB of the machine. Right? So maybe we can say that since Y does not include the system input, which is what? What was the system input over here? It was X, all right? System input X, right? Since Y does not include the system in its equation, therefore, this is a Moore machine. All right? Okay? So everyone got the picture over here? When there is a system output and QA and QB, and the system output is only dependent on the states of the states of your flip-flops. There is no influence from the system input. Okay? All right. Now, obviously, the Mealy machine is the opposite. But we'll come to that in a short while. We'll look at question 1. All right? Okay. All right. Now, there is a slight difference in how we draw our state diagrams. The Moore state diagram, this is easy. Moore state diagram is basically like what we've been drawing it, right? The Moore state diagram is like what we've been drawing it. Let's show you guys. If you remember the answer for question 1, remember this question 1, we did this particular problem, and then from the problem we did the equations, we filled up the state table. The final answer was a state diagram, right? The final answer was a state diagram. And that state diagram, sorry, not question 1, question 2, right? Referring to question 2. Question 2, right? Okay. The final answer was a state diagram. Remember that? Okay? That's a Moore state diagram. So let me just draw a quick one. I don't know if it's the same answer or not, but Moore state diagram would look just like a normal state diagram which we've been doing. Right? So 0, 0, 0, 1, 1, 0, 1, 1, you know, normal state diagram which we've been doing. That's 1, 0, 0, 1, right, 1, 0, 0, 1, 1, 0, 0, 1, right? Okay, like our normal state diagram. Looks pretty normal. Like our our examples. And this is from the in-class problem, right? Like our examples in class. Okay, now, let's move to mealy. Mealy is slightly different, opposite in fact. But the state diagram, this state diagram is like what we've been doing. So that's why you guys have done so many state diagrams so far. All right, now, let's move to mealy. But the main point is this, guys, once again. A Moore system, right, that's the title, it's like a classification. Like for example, you have a classification in mathematics. Is this a continuous system or is this a discontinuous system? Or is this even number or is this an odd number? That's just a classification of a number, right? Or is this a rational number or irrational number? Is this a NaN system or is this an NO system? Different classification. Same thing goes here. I'm just teaching you the definition of one of the classifications. So the first classification is the Moore one. Moore means that the system output, which is Y in this case, right, does not have any direct influence from the system input. It's only dependent on the current states of your flip-flops. All right, now, and the state diagram looks like this. Now let's look at thing now. Let's look at mealy. Let's look at mealy. I think I made a mistake somewhere. All right, okay. Mealy circuit or mealy state machine. Now, mealy state machine. The mealy state machine, the output, the system output is a function of the present state as well as the system input. Right. Now let's say refer to question 1. Refer to question 1 in our in-class exercise. Refer to question 1. Okay. All right, now I want you to now deduce what is the equation for y over here. What is the equation for y? Right? Yeah, y is equals to xqa. So let's just write this down. Y is equals to xqa or x bar qb bar. Right? From here. You see there was a system output called y, and we were able to deduce that the output y is equals to xqa, right? xqa or x bar qb bar. Set what I've written over here. Now have a look at it. Can you see the equation for y is influenced by the system input? Yeah? So therefore this is a mealy machine. This is a mealy machine. Now since the derivation for y or the equation for y is influenced and contains system input x. This is a mealy machine. Okay? right? Can you see X is present, right? Can you see X is there? These guys were present, all right? Okay? So that's a milli machine, that's a more machine, all right? Okay. Okay, now, let me draw the state diagram. Thank you. Okay, let's draw the state diagram. I made a mistake early on, guys, sorry. I made a mistake early on. The state diagram for milli machine is straightforward. So there was an error in the more machine state diagram. So the state diagram 0, 0, 0, 1, 1, 0, 1, 1. Yeah. All right. Okay. The state diagram is normal. Right? This is where I made the error. Apologies. Right? We'll correct that now. So, like state diagram for our milli machines look normal, like our examples. Set? Okay? Now, let me draw the more one. I think that's where I made the error. So, more state machine. So, let's just give you time to note this down. If you're okay. Okay? All right. Okay. And we'll have a look at it in a short while. We'll do some in-class exercises from the notes. Set? Okay, can you guys just cancel this, guys? Can you guys, I'm flipping the page over to the more state machine. Can you guys just put a line through here? Like that? Okay, I'm going to draw the more state machine. All right, now, when you come to this topic here, basically, what is in summary? If somebody said, if the question was, how would you differentiate, in English, if somebody said, explain, how would you differentiate between a milli-state machine and a more state machine? So basically, what is it? It's the difference is the way in which the system output is derived. If the system output depends directly on, if it depends directly on X, and X is involved in the, if the system input is involved in the derivation of system output, then that is a milli machine. And if X is not involved and the output of the system output is only dependent on the current states of the flip-flops, that's a more machine, all right? So that's a way to think of it. Just write that sentence down if you want, but you should be able, there could be a question in your short test too, or in your final exam to differentiate between how you derive, how you know, right? Explain, and so forth. Now, hey, state diagrams. Let's come and talk about the state diagram. I made a mistake early on. Now, the more state diagram. The more state diagram basically looks like this, guys. Okay. This is the system input. So in fact, if you now reflect back, we have to correct one of our earlier in-class exercise problems. Now, if you look at this system, the way we used to draw our state diagrams, what I did was I deliberately made that particular error, and then I'm correcting you now. Because there's so much to learn when you come to sequential logic and you can get lost. So I taught you the easy way. Just do 1/2, or I mean 1/0 to show input / output, right? But with the more state machines, the output is shown actually in the bubble itself. Okay? These two, remember, what did we say about more? More machines directly, the output is directly only dependent on the states of the input or of the flip-flops. So the state of the flip-flops is affecting the output here. The state of these two flip-flops is affecting. So we put the output within the bubble. The output is within the bubble. So therefore, what can you say? Which problem did we make a mistake in? I think the tutorial one, no, in the tutorial, let's just have a look at the tutorial problem. Let's have a look at the tutorial problem and we'll finish off very shortly, guys. Okay, can you tell me, let's have a look at this one. Is this a milli machine or is this a more machine? It's a milli machine because if you look at that X, yeah, so a state diagram will be looking like that, right? Okay, let's come to our notes. You'll see some more in our notes. Sequential circuits. All right. So now we've done this. This is basically just some basics, right? This is what type of state diagram is this? Is this milli or more? Yeah. By looking at the state diagram, you should be able to tell whether it's milli or more, right? Okay. There's one more thing called the timing trace, which is, again, guys, just to let you know, one of the things about digital electronics is that what we are trying to do is a lot of the same system, we want to show it in a different way, but it's the same system. Like for example, right in the beginning of the semester, you had a look at, let's say, a digital circuit, AND and OR gates and all that. Another way to put that same system is to put it in Boolean algebra. You trace it and you say, oh, output Y is equal to so-and-so equation. Another way to show the same system is to put it in a truth table. Another way to put the same system is to, from the truth table, you reduce it to a sum of products. That's a long equation. Or you can put it as product of sums. Or you can put it as a sum of minterms. Or you can put it as, product of max terms. Or you can put it in the Kano map. Or you can reduce the Kano map and then do groups and then say, oh, this is the minimized sum of products. You see what I'm trying to say over here. There's so many ways to show the same system. It's all the same system, just differently. So same thing goes over here. We have state table. We have state diagram. We have the circuit. The circuit shows the same thing as the state table, which shows the state thing as the same state diagram, which shows the same thing as the timing trace. Right? And the timing trace is just easy. It's, once again, you just look at your current input, you look at your current state, and you predict your output. Alright? So it's basically, this here, the timing trace comes out from your state table. Alright? Once you've done your state table, you can then, just like how you do your state table, you can transfer that knowledge and then draw your state diagram. Yeah? Or if you've got a state diagram, you can transfer that knowledge and draw your state table. The same thing goes over here for timing trace. All right, just take a note of that, and I'll let you guys have a look at the example. These examples of some timing traces over here. So anyway, we were discussing about state diagrams. This here is a milli. This here is a milli again. All right, okay. Now let's look at the next one. These are basics again. So all the basics. All right. We've done all this. We'll do this next week. Okay, these are all basics. Hey, all right, let's have a look at this problem, guys. Can you tell me, what sort of circuit would this be, milli or more? Okay, let's look at this X. Okay, let's look at the Z. You've got to look at the output Z, eh? Z, let's go backwards. backwards, that there, okay. Z. No, this is, what can you tell me about this guy? Z is only more, because the only output, Z is what? Z is equal to Q2 bar. Q2 bar. Alright? It's equal to Q2 bar. Alright, let's now, by the way, yeah. Q2 prime means Q2 bar, okay? I think that's quite obvious. Let's have a look at this guy. What state diagram is this representing? More, alright, more. Because when the flip-flop, let's say flip-flop B and flip-flop A was 0, 0, the output Z was 1. Alright, okay. Okay, now let's look at this circuit. What can you tell me? Z, let's go backwards. That's coming from A, that's coming from B. That's a more. In fact, the answer is there already. Alright, anyway. Timing trace, guys, I won't teach you guys word for word how to do timing trace, but it's exactly how you, it's just another translation from the state table into our, and state diagram into a timing trace. Same thing, just another way of drawing it. Okay, let's have a look at this one. Let's have a look at this one. The output